So when it comes to financial mathematics, of course, it involves financial growth, which is simple interest and compound interest.
Yeah.
And then there is financial decay, which is the straight line method, which is the simple decay. And that's the formula.
Yeah.
Then the compound decay, sometimes called the reducing balance method. And that's the formula there. And if the annual interest that is quoted, which is the nominal interest, is compounded more frequently than once a year, the effective interest rate will be higher than the nominal interest rate and is determined using the formula. So that's the formula of determining the nominal interest rate, rather the effective interest rate. And then to determine the amount accumulated after an investment has been growing with compound interest, that is compounded K times per year, divide the quoted interest rate by K and multiply the number of years by K. Of course, already you know this. When more than one transaction occurs, draw a timeline to visualize what has happened over time. Remember to take all values to any one moment in time, that is before adding or subtracting the values. Use the logarithmic that total of money in equals total of money out. Then when taking values back in time, you are finding P for an unknown value of A. So already all of this, you know them. And some of these questions, we tackled them in our previous session. So for every question that we tackled previously, I'll skip it. And because when you look at question 1, Porsche buys a motor car for 150. The car depreciates at a rate of 12% per annum. What is the car worth 5 years if depreciation? So the straight line method, I know that one you can easily do it. And then reducing balance method. So it's just a matter of substitution. You have the value of P, the I here, and the N. So the substitution would simply be easily done. Then 2. Question 2. Zweli invests 12,000. So this is our P in a savings account, which pays 9% per annum compounded monthly. Calculate the value of his investment in 10 years time. So in this case, using the compound interest formula, you have the value of P, the value of I and N. Could simply substitute and get the answer, except that you have to divide your I by 12 and your value of N multiplied by 12. So this is similar to what we did in the previous session. Then question number 3. Question 3. 100,000 is invested for 5 years at an interest rate of 16% per annum, compounded quarterly. Thereafter, the accumulated amount is reinvested for a further 6 years at an interest rate of 15% per annum, compounded semi-annually. Calculate the value of the investment at the end of 11 years. So I think we need to work out this question. It's investment with compound interest. So for the first period, our principal amount of 100,000 is invested at a rate of 16% compounded quarterly. This is for the first 5 years. So that would be your 5 times 4, which is 20. And then that amount grows to 219,112.31. Then this amount here is again reinvested 219,112,32 is invested in an account that earns 15% compounded semi-annually for 6 years. So that is 6 times 2, which is 12, and the overall would be 521,877,23. Alternatively, instead of breaking it down, candidate would use the same principal amount of 100,000, then first grow it at 16% compounded quarterly over 20 quarters, then times a bracket whose interest is going to be 15% compounded half yearly, and then to the power of 12. So in both cases, we end up with a final investment value of 521,877.23 rands. And then we go to question number 4. It talks about Sarah. Sarah deposited 15,500 into an account. So 15,500 was invested into an account, so that's the value of P. The interest rate for the first 2 years is 10% compounded quarterly. It then changes to 8.5 per annum compounded monthly for the next 3 years, and then changes to 11% per annum compounded semi-annually thereafter. How much money will she have in her account after 7 years? So it's the same account, but there's a change in the interest rate.
Yeah.
So I'll draw a timeline here for visualization purposes.
Okay.
So at T0, at the beginning of time, 15,500 was deposited into an account, but it earned an interest of 10% for the first 2 years. So this is going to be T2. The interest here is 10% compounded quarterly. Then for the next 3 years, so 2 plus 3, that will put us at T5. The interest rate changes to 8.5% compounded monthly, and then finally until T7 it changes to 11% compounded semi-annually. So we have a change in the interest rates. So the 15,000 would grow for the first 2 years, earning the interest rate compounded monthly. So that would be N2 times 4, which is 8 quarters. Then at T2, it will earn a new interest rate, which is compounded monthly. So from T2 to T5, those are 3 years. So N would be 3 years times 12, which will give us 36 months. And then finally, it will grow at an interest rate of 11% compounded semi-annually for the next 2 years. So that would be 2 years times 2, which give us 4 half years. So using the compound interest formula to the power of N there. So it's the same principal value of 15,500. First earning the interest of 10% compounded quarterly for the 8 quarters. So now we are at point T2. Then it earns an interest of 8.5% compounded monthly for 36 months. So now we are at T5. And then finally it earns an interest of 11% compounded semi-annually for the last 4 half years. and this would give you a total of 301,000. I think it's 30,163,88. So that's how much would finally be into the account after a period of 7 years. So now this is with the changing interest rates for just one transaction. Then let's go to question number 5. Question number 5. Paul deposits 80,000. So this is the principal amount there into a savings account, paying 13% per annum compounded monthly. After 5 years, the interest rate increases by 4%. 3 years later, the interest rate decreases by 1%. So let's draw the timeline to visualize what is happening. So at the beginning of time, 80,000 was deposited, and it earned an interest of 13% compounded monthly.
Yeah, over
5
time.
years, 5 years later, so that is 85, the interest rate changed. It increased by 4. So that means 13% plus 4%, that will be 15%. So it increased by 15, is it? By 4, that would be 17, not 15. So it increased by 15%. So still monthly. So this would be I would equal to 17% compounded monthly. Then 3 years later, 3 years, so that will be 5 plus 3, which give us T8. It decreased. So from 17, it decreased by 1% to 16%. So this would be 16% compounded monthly. And the investment runs for 10 years, so till 10. So the 80,000 is in the same account that is earning different interest rates. So for the first 5 years, our N will be 5 times 12, which will be 60 months. And then for the next 3 years, that's from T5 to T8, it will be 3 times 12, which is 36. And then for the last 2 years, N would be 2 times 12, which is 24 months. So using our compound interest formula, the principal amount is 80,000. It grows at an interest rate of 13% compounded monthly for the first 60 months. Then the accumulated amount grows at a new interest rate of 17% compounded monthly for 36 months. And that accumulated amount then grows at another interest rate of 13% compounded monthly for the last 24 months. And then that will give us a grand investment value of 384,000. I think it's 348. It's the other way around. So I need to clear up. So it's 348,222,14. So that's how much would be into that account after 10 years. So question 4 and question 5 are focusing on one principal amount that earns different interest rates. So here the interest rates are changing, but at only one principal amount. But then at times, or in most cases, we have different transactions into the account. For example, you deposit money into the account today, then after some time you withdraw it, you withdraw some of it, and then maybe after some time you get another deposit into the account, and then you withdraw. So the withdrawals and the deposits, and then still there is a change in the interest rates. So you look at a scenario where you are having several deposits and several withdrawals, and the changes in the interest rates. And question 6 gives us a picture of that scenario. Mvelo decides to start an emergency savings account for the future. He deposits 6,000 into a savings account. 3 years later, he deposits a further 8,000 into the account. So it's the same account. 4 years after this, he deposits a further 10,000 rands into the account. So these are 3 deposits. The interest rate for the first 4 years is 14% per annum compounded semi-annually. For the next 3 years, the interest rate increases to 15. Not by 15, but increases to 15.
To 15, yeah.
Yeah, to 15. Compounded quarterly. So we have 2 interest rates within the same account, which has 3 different transactions. So to visualize this, we need our timeline. So at the beginning of time, 6,000 was deposited into the account. 3 years later, so that is a T3, this person adds 8,000 into the account. And then 4 years after this, so 3 plus 4, that would be T7. The person adds 10,000 into the account. 10,000 into the account. And the question is asking us to calculate the value of the savings at the end of the 7-year period. So that means our final point is T7. So the 6,000 will be into the account until the end of 7 years. The 8,000 will be into the account till 7 years. And the 10,000 also be there at the end of the 7-year period. Then the interest rate, 14% for the first 4 years. So at T4, we have the interest rate there, and it is 14% compounded semi-annually. And then it changes to 15% compounded quarterly. So the 6,000 would earn the interest of 14% compounded semi-annually for 4 years times 2, which is 8 half years until T4. Then it will earn an interest of 15% compounded quarterly for the next 3 years times 4, which is 12 quarters. The 8,000 would earn the interest rate of 14% compounded semi-annually for 1 year times 2, which is 2 half years just. And then it would earn the 15% compounded quarterly for the next 3 years times 4, giving us 12 quarters. So, and the 10,000 doesn't earn any interest because it was deposited at the end of the 7-year period, and we actually finding how much is into the account on the day the 10,000 was deposited into the account. So using our compound interest formula, we work with the 6,000 and 14% compounded semi-annually for the first half years, and then it grows at an interest rate of 15% compounded quarterly for the next 12 quarters. Then plus, because the 8,000 was added, so plus, it was added into the account, 8,000, which earns interest of 14% compounded semi-annually for 2 half years, and then it earns an interest of 15% compounded quarterly for the next 12 quarters, and of course plus the 10,000, plus the 10,000. So we compute all of this, and finally would have a total value of 40,282.08. So this is how much will be into the account at the end of the 7-year period. The 6,000 and interest, actually 2 interests, and also the 8,000 and 2 interests, but the 10,000 did not earn any interest because we are calculating the accumulation of the investment until the day the 10,000 was invested. So that is changing deposits or changing transactions with changing interest rates. Then we go to question number 7. We go to question number 7. NOMC deposits 20,000 into an account at an interest rate of 9% per annum compounded quarterly. 3 years later, she deposits another X amount, so that amount is unknown. 2 years after that, the interest rate changes to 10% compounded annually. She withdraws 12,000 at the time that the interest rate changes. At the end of 8 years, she has 43,062.27 rands into account. Determine the value of X. So we need the timeline to help us visualize this. So at the beginning of time T0, 20,000 was deposited into the account. 3 years later, she deposits another X rands. So at T3, X rands is added into the account. X rands is added into the account. She withdraws 12,000 at the time that the interest rate changes. So when does the interest rate change? 2 years after the interest rate changes. Okay. NOMC deposits 20 into an account at an interest rate of 9% per annum compound quarterly. 3 years later, she deposits another amount of X rands. 2 years after that, meaning 2 years after depositing X amount, so that would be at T5. So at T5, that's where the exchange rate, rather the interest rate changes. And at the time when the interest rate is changing, there is a withdrawal of 12,000 from the account. And then at the end of the 8-year period, a T8, there is an amount of 43,062. So 43,062,27. So first, the 20,000 is assumed to be into the account till the end of the period. Similarly with the X amount, and then withdrawing the 12,000, meaning the 12,000 could have been into the account. So when you withdraw an amount from the account, you also lose the interest that amount would have gained if it was left into the account until a given period. So we shall have to withdraw or to deduct the 12,000 together with the interest it would have earned. First, the interest rate is 19% compounded quarterly. So it's 9% compounded quarterly. Then it changes to 10% compounded annually. So meaning it is effective, which is just 10%. So that means for the 20,000, it will first of all be from T0 to T5. This will be 5 years times 4, which is 20 quarters. And then finally N will be 3 because it's years. Then X, T5 and T3, the difference is 2 times 4, which is 8 quarters. And then finally this will be 3. And the 12,000 would have been into the account for a period of 3 years. So let's work it out, still using our compound interest formula. The 20,000 and interest of 9% compounded quarterly for a period of 20 quarters. And then it earned another interest of 10% compounded annually for 3 years. Then plus the X amount, which earned an interest of 9% compounded quarterly for the first 8 quarters, and then earned interest of 10% compounded annually for the last 3 years. Then minus the 12,000, which could have earned an interest of 10% compounded annually for the 3 years. And all these transactions, the deposits and the withdrawals, leave us with a balance into an account, and the balance is of 43,062,27. So we have created an equation that we need to solve algebraically. So you'd work out the 20,000 and subtract the work out of the 12,000. Then you subtract it from the 48 and then divide by these two brackets. And when you do that, you finally get your X being 11,000 rands. So the amount that this person deposited was actually 11,000 rands, but you can only get that when you first of all use the timeline to give you the financial picture or the transactional picture, which then helps you to create the equation that you can solve. Then question 8. So far question 6 and question 7 fall within the same basket. Then question 8, let's see what happens. Phil Lemon takes out takes out a loan of 50,000 rands to renovate his house. Now, this is a loan. Interest on the loan is 9% per annum compounded monthly for the first 2 years, and then changes to 9.5% compounded half yearly. He makes a payment of 20,000 1 year after taking out the loan, and another payment of 25,000 2 years later. How much will he still owe on his loan 4 years after taking out the loan? Now this is to do with the loan. Remember, a loan earns interest. A loan earns interest by all means. So at the beginning of time, we got a loan of 50,000. So we got a loan of 50,000. According to the lender, which is the financial institution, they expect you to pay back their money with interest. They expect you to pay back their money with interest. So this loan will grow and earn interest, and you have to pay it back. So let's deal with the transactions first before the interest rates. He makes a payment of 20,000 1 year after taking out the loan. So at T1, this person makes a payment of 10,000, and another payment of 25 2 years later. So 2 years later, that would be at T3. This person makes a payment of 25,000. So this would be 25,000, and he has to pay an outstanding. Let's say the outstanding would be X amount. The 20,000 is part of the loan of 50,000. So the question is, what amount of the 50,000 gains interest to make an amount of 20,000? That's what we need. What amount of what amount of the 50,000, which is the loan, and interest that made Philemon to pay 20,000. Similarly, the 25,000, we work it back in time. What amount of the loan, which is 50,000, and interest such that Philemon was to pay back 25,000, and then the final amount, which is X amount, which value of the loan, or which amount of the loan necessitated Philemon to pay the final amount. So when we work these three transactions back in time, the values we get are those values without interest. From the compound interest formula, which is A equals P into 1 plus I to the power N, A represents the accumulated amount, and then P is the principal amount, the original amount. So in this situation, this is the loan. Okay, P is the loan, and we are trying to work in time. We are working back in time. So algebraically, if you divide by the bracket, this gives you P. And then applying one of the laws of exponents, that if you have A to the power of negative to the negative A, and this is the same as 1 over a to the power of positive n. So applying this law of exponents, we shall actually have a brackets 1 plus I to the power of negative n as equal to p. So to calculate the principal amount, we are going to use this formula, which is p equal to a into 1 plus I to the power of negative n, because we are trying to work in time. We are calculating back in time. We are trying to take off the interest. So the original amount of the loan was 50,000. This should equal to the accumulated value of 20,000 plus, oh, we forgot to analyze the interest rates. The interest rate is 9% for the first 2 years. So this is a T2. The interest rate is 9% compounded monthly. And then it changes to 9.5% compounded half yearly. So that means the 20,000 we shall have n equals 1 year times 12, which is 12 half years. And then the 25,000, we shall first of all work it out for 1 year times 2, which is 2 until there. Yeah, this is supposed to be 2 non-12 because we are dealing with half years.
Yeah.
Until T2 there. And then work it at, this is going to be 2 years times 12, which is going to be 24. Then the X amount, this will be n equals T2, T4, this will be 2 times 2, which is going to give us a value of 4, which will be a value of 4. What have I done? What have I done? I think I need to, okay, T2 there. So this is I equals 9% compounded quarterly. I think it's quarterly, no, monthly. So you divide this by 12. So this is going to be n equals 1 times 12, which is 12. And then this is going to be I equals 9.5% compounded half yearly. So this is 1 year times 2, which is 2. And this will be n equals 2 years times 12, which is 24. Then for the X amount, it's going to be n equals 2 years times 2, which is going to be 4 half years. And this will be n equals 2 years times 12, which is 24.
Yeah.
So for the 20,000, it is experiencing only one interest rate of 9% compounded, rather monthly. So to the power of negative 12, because we are calculating back in time. Then plus the 25,000, which so we are working it back in time. So we'll start with a 0.095 divided by 2 to the power of negative 2. So that means now we are at T2, where the interest rate now changes to 9% compounded monthly, and this will be to the power of negative 24. Then plus the X amount, which is the final amount, which should be 1 plus 0.095 out of 2 to the power of negative 4, and then times 1 plus 0.09 out of 12 to the power of negative 24. So we have created the equation, and then we have to apply the algebra. So when you work out the algebra, this will finally give you a value of X of 18,252.73. So that's the final amount. And when you add these two amounts, the 20,000, the 25,000, and the 18,252.73, you can see that at the end of the day, there is interest paid to the loan. So all in all, this person paid back 63,252 instead of the 50,000. So that's how that question needed to be approached. Then question number 9, Robin invests 30,000 at 16% per annum compounded quarterly for a period of 15 years. For a period of 15 years. Convert the nominal interest rate of 16% compounded quarterly to the equivalent effective rate annual. So using our effective interest formula, IM over N to the power of M. So this is 1 plus I effective equals 1 plus 16% divided by 4, then raised to the power of 4. And when you apply the algebra, you transpose the 1, punch everything in a calculator. This gives you 16.99%.
Okay.
And then 9.2, now use the effective rate to calculate the future value of the investment. The investment is of 30,000. So shall use our A equals P into 1 plus I to the power N, 30,000 into 1 plus the effective interest rate, which is 16.99% to the power of 15. And this gives us a value of 31,000. Is it? No, 300,000, I think. It is 300,015. 315,756.55. So that's how much the investment would be. But still, you can double check using the nominal interest rate. You'd still end up with the same value. This will be 30,000 into 1 plus. Now use 16% divided by 4 because it's quarterly to the power of 15 times 4 quarters. It will also lead to the same value.
Yeah.
Yes. So that is it with the grade 1, rather the grade 11 section of financial mathematics.
Yeah.
Then next is the investments and loans involving annuities.
Okay.
Yeah, so annuities. So there's investments and loans. So we start by defining an annuity. An annuity is a series of equal investment payments or loan repayments, because a loan, you are repaying a loan. You're repaying someone's money. Yeah. Loan repayments at regular intervals, subject to a rate of interest over a period of time. So that is an annuity. For instance, people who buy houses, they get what they call the home loans or the mortgages, I think.
Yeah.
So you want to buy a house and the house is valued at 600,000, of course, which you don't have in cash. So you reach out to your bank, the bank approves. The bank pays the house for you. it pays it pays whoever is selling the house, it pays them the 600,000. So now you have to pay the bank
Bank.
that
Yeah.
100,000, and the agreement is okay. No, don't worry, it's okay. You can pay 8,000 every month for 20 years.
Yeah.
So every month you keep on paying 8,000, 8,000. Another situation is maybe for retirement.
Yeah.
People strive to save for retirement. And then, okay, let me go back to the other point of you paying the loan to the bank. You agree with the bank that you should pay back 8,000, but remember the 8,000 also caters for the interest the bank charges you. So by the time you're done paying the loan in 20 years, you'll have paid more than the 600,000.
Yeah, correct.
That would be the interest. Now for maybe you're saving for future education or for retirement. In this situation, you're striving to have an accumulated amount in future. Okay, in future. So every month you deposit a certain amount into your account.
Yeah.
A certain amount into your account. And because the bank is receiving your money and is using it for its other investments,
yeah,
it has to pay you some interest. So if every month you're paying 2,000, that 2,000 has to keep on earning interest. So if it's for 10 years every month, so that you're looking at 120 transactions or installments, and each installment will be earning interest monthly. So those are some of the scenarios where you have annuities. So we focused on two annuities. One is the future value annuity. The future value annuity. And the other one is what we call the present value annuity. The present value annuity. So for today, let's start with the future value annuity. So with the future value, you are looking at having an accumulated amount in future. So in a future value annuity, money is invested at regular intervals in order to save money for the future. The magic of compound interest makes the investment grow in value, especially if the interest rate is above the current inflation rate. Typical future value annuities include retirement annuities, in which people save money each month so as to receive pension payments once they retire. And this is our formula here for the future value annuities, where X stands for the equal payments made per period, and I is our interest rate, and N represents the number of payments, paid or to be made. So example 1, Peter decided to start saving money for a period of 8 years, starting on 31st December 2009. At the end of January 2010, in 1 month's time, he deposited an amount of 2,300. He made his decision 31st December. That's when he decided. But he took action at the end of Jan. So you need to be very careful. A date when a decision is made may not necessarily be the date when an action is effected. So this person decided at the end of 29 but then he made action of depositing 2,300 at the end of January. So he made 2,300. Thereafter, he continued making deposits of 2,300. So this means every month is making a payment of 2,300. So that means the 2,300 is our value of X. And this is going on for 8 years. So in 8 years, if you're making 2,300 every month, how many of them are you supposed to make? So that would be 8 times your 12, which gives you 96 deposits or 96 payments in 8 years. The interest rate remained fixed at 10%, 10% compounded monthly. So it's 10% compounded monthly. How much will he have saved at the end of his 8-year plan, which started on 31st December 2009? So the plan started on 31st December, but it was effected on the end of January. So of course, in that situation, you write down your formula: 1 plus I to the power of n minus 1 over I. Our X is 2,300 into 1 plus 10% compounded monthly to the power of 96 minus 1 over 0.1 out of 12. And this would give a value of 336,216.46. And even when you look at the timeline shows you that, okay, T0, which is 31st December, he did not make any payment. The first payment was made after a month's time. So there are a total of 96 payments, and the duration of investment is 8 years, which is 96 months. So this one is quite simple, straightforward. Okay, so you decide today, but then you start paying afterwards. But then example 2 shows us a situation where a payment is made immediately. Sometimes payments are made immediately. For example, if we go back to this question, if this person decided to make a payment on 31st of December, so that means the 96 payment would add 1, which was add immediately, and this would be 90. $97. Jesse deposits 400 into an account paying 14% per annum, compounded half yearly. Six months after this, she then continues to make half yearly deposits of 400 into the account for a period of 9 years from her first deposit of 400. Calculate the value of her savings at the end of the 9-year period. So Jesse deposits 400 into a savings account, like today or like now. And then 6 years later, makes another deposit of 400. And he keeps on doing that until the end of 9 years. And he's doing this after every 6 months, meaning after every half year. So that would be 9 years times 2. This will give you 18. But remember, there is a deposit of 400 that was made immediately. So plus 1, that will make it 19. And that's what this statement is trying to talk about. That there are a total of 19 payments, and the duration of investment is 19 years. So it's 19.
Yeah.
That extra one payment is the one which was made immediately. And of course, you substitute into the formula 1 plus I to the power n minus 1 over I. Your x is the 400. The interest rate is unchanged, which is 14% compounded half yearly, now to the power of 19. The power of 19, and that would give that value of 14,951. SubhanAllah, power is gone. Not really. Can you hear me?
Mr. JJ?
Michael? Can you still hear me?
Yes.
Okay, power has just gone, and when it goes, the network misbehaves.
Oh, okay. Now I can hear you clearly.
Okay, that's good now. So there is a note here at the bottom that when a payment is made immediately into the account, the total number of payments increases by 1. So from n to n plus 1. Then example 3 is emphasizing that also. Diana has just turned 20 years old and has a dream of saving 8 million rands by the time she reaches the age of 50. She starts to pay equal monthly payments, equal monthly amounts into a retirement annuity, which pays 18% per annum compounded monthly. Her first payment starts on her 20th birthday, meaning as soon as she clocks 20, immediately she's 20 years. That's when she makes the payment. And her last payment made, is made on half of years. So you're 50 plus 20, that gives us 30 years times 12, which will be 360, but plus 1 because she made a deposit as soon as she clocked 20 on her birthday. And how much will she pay each month? Because her future value has to be 8 million. So of course, with our formula that
Mr. JJ?
I to the power of n, my future value is 8 million. Yes, Michael, network.
Can you hear me correctly?
Yes, I can hear you. Can you hear me?
Yeah, I think the network was just stuttering. It's okay.
Oh, okay.
Yeah.
Okay, let's proceed. So our value of F is 8 millions, and we are looking for the X amount. The interest rate is 15% compounded monthly, and our N is 360 plus 1, which is 361 over 0.15 over 2. And we need to get the value of X. So take you through the algebra. This is 8 millions. You cross multiply by our 15% divided by 12. Then divided by the square bracket, which has 1 plus 0.15 out of 12 to the power of 361 minus 1. And that's how we get our value of X of 558.41 rands. So that's how much this person is supposed to be depositing into the account every month. Then example 4 is also talking about the same.
Yeah.
A father decides to start a savings plan for his baby daughter's future education. On opening the account, he immediately deposits 2,000 into the account and continues to make monthly payments at the end of each month thereafter for a period of 16 years. The interest rate remains fixed at 15% per annum compounded monthly. How much money will he have accumulated at the end of the 16th year? So it will be, our N would be 16 times 12, but of course plus 1 because you made a payment